Next up is Paul Torcellini. Paul Torcellini is a professional engineer for commercial buildings research at the National Renewable Energy Laboratory. Paul is a key contributor in the development of the Advanced Energy Design Guides for ASHRAE, AIA, IES, and USGBC, including chairing the technical committees that produce the Zero Energy AEDG guides. Paul has been at NREL for 29 years and is a registered professional engineer holding a PhD from Purdue University. He is an ASHRAE Fellow and Distinguished Lecturer.
Got it. So Scott said before I have a limited time, and now he just says I have plenty of time. So you guys ready? Here we go. Okay. Adam handed me this morning's paper, right? Heat pumps touted as a way to cut emissions. So it's out there, right, in the regular press. All right, here we go. So let's start with, and we've heard some kind of big picture statements this morning. Both Ginger and Carrie talked about it. What do you think the future of buildings should look like, right? And especially with, how many was it? 34 New York cities, right, being built? What should they look like? And do we have some vision of what that should be? And then kind of the next part of it is, they're also going to confine me, I think, to a pretty narrow spot here. So what is in our span of control? Like, what do we make decisions about every day? And there may be some common ones here. Do you drive an all-electric car? Do you have a hybrid that you only use in electric mode? Maybe, especially in New York City, you don't have a car at all, right? And that you're able to conduct life that way. Do you live in a zero-energy home or work in a zero-energy building? Maybe something a little bit easier to think about is, do you only purchase local or organic food? There was some discussion in the previous one about agriculture, and Ginger talked about food supplies. The impact of food supplies is huge, right? And so do you think about those things when you make decisions? Here's the softball one, right? Are all of your lights LED in your own home, right? We've got to start somewhere. And so if you think about it and you say, how many of these things can you say yes to? And what would it take to say yes to those things? And if you can't, why is that? What are those barriers that all of us who have come to this conference that are passionate about moving in this direction, we've got to start somewhere, right? And so what is it going to take to say yes to all these things? Even something like, I got my ASHRAE water bottle here, right? How many of you brought water bottles today? How many of you brought your own coffee cup, right, for the beverage that's being served here today, right? All those things matter, but you have to kind of internalize it first to go further. Why is it important? Just as a refresher, buildings, 40% of the nation's energy, right? 26% transportation, about a little less than a third. A lot of that is getting us to and from buildings at the end of the day. A third of it is industrial. A lot of that is to make stuff for buildings. And as we talk about the scopes of emissions, it's amazing how much of it is more than just what we call buildings, but the entire pie is going into buildings. But the other part of it is that it's still the biggest pie is operational energy for buildings. And so that is really one of the key focus areas here. A good chunk of that is natural gas still, mainly heating, a little bit of cooking and other things. And then that purchased electricity part, and where does that electricity come from? And I want to talk a little bit about that as we go along here. And so 80% of the fuels are fossil fuel derived in some way, right? In the Northeast here, we've got a little higher percentage of nuclear. And renewable energy is coming along, but it's still a pretty small piece of that pie at the end of the day. So, and Ginger kind of alluded to this before, is that our energy pie is still growing. the growth is faster than we can deploy energy efficiency. So we can go out there and talk about how energy efficient our buildings are, but we're adding buildings faster than we're deploying energy efficiency, right? And so even though you can talk about, oh, maybe the EUIs are going down, the pie keeps getting bigger as we go along here. In fact, if we go back to, say, 1980, which is kind of where, so I'm also kind of this early teenager of the late 1970s as well, right? And I remember gas jumping to $1.60 a gallon. And if you put it in the context of today's dollars, that's somewhere around $5 a gallon. So it's, again, kind of cheaper today than it was when I started driving. And that's about when we started thinking about all this energy stuff, right? Standard 90 was getting put out there, right? And if you go back to 1980 and say, if all the buildings we built were zero energy, i.e., producing as much energy as they consume, or at least having a source of that energy, maybe a renewable energy farm somewhere else, but kind of having that one-to-one match, you know, we'd use about half as much energy today in the commercial sector that we do today. Now, that curve has leveled off, right? And there was a little dip downward for COVID on the commercial side. But if you take a long-term rolling average, 5-6 years, that number is still incrementing up. And to kind of go consistent with that, 34 new New York cities, you know, if the growth rate is 1%, how long does it take to double the energy, right? Somewhere between 60 and 70 years. So even a very small increase, you know, makes the pie bigger over the time frames that we're talking about in trying to accomplish some of these goals. The other piece of it is every decision you make has some energy or environmental impact to it, right? I already mentioned my water bottle, right? Coffee cups, things like that. Those are little decisions, but all of us make decisions. They could be design decisions, which impact larger buildings. It could be some of those other things I mentioned, where we live, how we get to work, whatever those pieces are. Think about it that every one of those decisions has an energy and environmental impact associated with it. And as a result, if you want to figure out what we're going to do in the future with buildings, how long do buildings last? How long has this building been here? You know, walk up and down Broadway and say, how long have those buildings been there, right? If we want to figure out how much energy is going to get used in the future in the buildings, look at what we're designing today as a starting point, right? Because those decisions you're making today will mortgage the energy futures of this country and of the world, right? And that is a pretty significant piece of it. Now, people on the grid side, and we hear about greening of the grid and all these kinds of things. When the grid planners plan for how to develop out electrical infrastructures, what do? They try to forecast that based on what? What has happened in the past? The electrical grid is, and in fact, the oil grid and natural gas grids and all those are kind of responsive to how we've designed buildings in the past. It's not the other way around. Okay? And so again, if you want to change how the utility grid looks in the future, we've got to rethink and change how buildings use energy. So, you know, all of this is about decision making, right? And there's so many ways of putting the puzzle together. This is Isaac. At the time, Isaac was 3, and his dear father put his puzzle together. Now, I used all the pieces in the puzzle, and I put them together. But if you're pretty closely looking, it's not quite right, right? Florida's kind of in the middle of the country is the obvious one. And it's interesting to me how easy it was to put the puzzle pieces together and say, yeah, we've got a building. It's functional. It works. Does it really? And the 3-year-old is like, Daddy, the puzzle is wrong. You can't do that. And I was like, hold it up. I used all the pieces. There were no holes. What's wrong with it? Right? And the 3-year-old, who, by the way, is a junior in college, says, you know, Daddy, it's wrong. And what do we do? So design is really about making lots of decisions. but you need the motivation sometimes to make the right decisions. And who are the decision makers? This room is filled with decision makers, right, on buildings. Who else is involved in the decision process of buildings, right? And how do we engage them in part of this discussion? One of those things is setting goals, right? Measurable goals are always better, right? You can be very vague. You can say, oh, I want a green building. Everybody know what that means? We'd probably have however many opinions. Maybe that should be the continuing ed question, right? Everybody know what that means? And we all come up with the same answer? Probably not. So then we start getting more specific, right? There are things like LEED that really helped kind of define that industry in the 1990s, right? And thinking about what that meant, right? We've got codes and standards that Carrie talked about that try to define and put some boundaries around that, right? You know, ASHRAE standards, right? Design a building that uses 30% less energy, right? That's a little bit more specific, but it's interesting to me, right? Here is my standard up here. Here is my 30% building right here. What's the easiest way to achieve 30%? Oh, let's fix the baseline, right? And make it higher. And yet we focus all this time on figuring out what this baseline is when we really should be figuring out what? How to get that building to use less energy. How to get the building's meter to spin slower. Which is why I really like absolute goals. Energy intensity, or use intensity is one of them. Design a building to use less than 25,000 BTUs per square foot annually. Right? That is something we can measure at the end of the day and know that we have hit the goal. Really, when we talk about a zero energy building or a zero emissions building, it's the same thing, right? That we've set a goal that at the end of the day, we should be able to measure and say, yep, we got there, or no, we didn't. All of these things, you know, when you've got a goal, I used to do a lot of teaching, right? Students would come into my class and they'd say, how many points do I need to get? Whatever grade they thought they needed to get, right? Why is that? It was a goal, it was a motivation, it was something they could measure at the end of the day. All of these are about influencing people and decisions. So what are zero energy buildings, right? And we can talk about what the kind of the carbon and emissions piece of it is with this. Conceptually, and why do we care about all this? It's a building that has no adverse energy or environmental impact. And then when we talk about operational, right, because of its operation. How many of you have the new Amazon product called the carbon meter? You hold it in front of your building and it tells you what its environmental impact is, right? What's the problem with that, right? We really can't measure that. We can't do that. And so what has happened is, what can we measure? Energy, right? The meter spins, you put oil in the fuel tank, natural gas goes through a meter, it's something we can measure, and so energy consumption has been a long-term surrogate for energy impact, for environmental impact, right? And that could be everything from early on, air pollution, water pollution today, to emissions from the building. All of these come down to where is the boundary and what am I going to measure? It's interesting that we do very strategically think about energy flows. All right, lecture Thermodynamics 101. Energy can't be created or destroyed. Therefore, all buildings are, if you measured all the energy flows, yeah, zero energy, right? So what's the big deal here? Well, we're very careful in what we measure, aren't we? As those things that have environmental impact, right? And we've done that for a long time. In fact, we're really, really good at doing that. And so that becomes the important aspect of zero energy, right? So I've got a little fat building sitting here that's consuming energy through all of its normal uses. And a real popular thing is, oh, I'll stick a PV panel on and I'll tip that balance a little bit. Well, usually that's not good enough and I have to thin down my building, don't I? right, in order to get that balance to work. And so what we strive for is reduced consumption, and then ideally, it would be on-site energy. Now, you're like, Paul, you have left the farm in northeastern Connecticut, and you have arrived in Manhattan. Look around, and what's the problem in New York City? Right? Probably not going to happen. But that energy still needs to come from somewhere, doesn't it? Okay? And so you can fly, one of my favorite airports to fly in is like Charlotte. And when you fly into Charlotte now, what do you see? Solar farms, right? Powering buildings that don't have enough capability locally, right? It is interesting. We did a study, 16, 17 years ago now, and we actually did an analysis on the commercial building stock in America and realized that we really have enough roof area to power it. So switch from flying into Charlotte to flying into Newark, and what do you see all around Newark Airport? Lots of warehouses, right? And interestingly, there's enough roof area in all those buildings that we can kind of solve the big city problems as well. 2016, there was a definition that DOE came out with energy efficient building, where on a source energy basis, the actual delivered energy is less than or equal to the on-site renewable export energy. Really, we've kind of expanded that thinking a little bit, where it might not be on the building, but what is that building's footprint at the end of the day? Well, it might be one of those solar farms in North Carolina. It might be rooftop solar from these warehouses in Newark, right? And that's okay, right? But it's all about, if we want to solve the problem, it's got to be a balance. What's the easiest way to achieve that balance? Is not to put more online, but to use less in the buildings. If we took our buildings and cut their energy in half, what would happen overnight to our renewable energy supply? It effectively would double, right? And so again, it's all about this balance. We've looked at solar radiation data maps and actually translated that back to EUIs for buildings, and we just picked a 2-story building. Some are 1, you get to Manhattan, they go this way, a lot more, right? And so depending on where the US are, just looking at solar hitting your property, which really is the energy that you're kind of entitled to, right? The numbers are somewhere between 44 in the Southwest. When you move up to this part of the world, something under 30,000 BTUs a square foot is a good starting target to think about, and I'll talk a little bit later. We should actually be less than that. So, we didn't get any sequencing here. Well, that's too bad, because now you know the answer. So, let's go to we've got 2 lines on this axis, right? Every decision you make has some energy impact, right? And so you can either go to the right of the blue line, the vertical blue line, or to the left of that line. Likewise, every decision you make either costs money or saves money. Everybody agree with that? I mean, if that decision is perfectly cost neutral, then you sit on that horizontal line. And when you put those 2 on a diagram, you get 4 quadrants out of this. So let's start with quadrant 1. In order to save energy, what do you have to do? Spend money. Everybody agree with that? What are examples of that? Better chiller, more insulation in the walls, right? And how do you decide whether those are good decisions or not? Payback, right? You do some kind of return on investment. We, as engineers, loved that discussion, and we prioritize all these things and all the rest of it, right? Now, think of some things. Let's go to quadrant number 2. Are there things out there where you can spend money and waste energy. If we were focused on spending money and saving energy in quadrant 1, are there things that we can do that spend money and waste energy? Any examples? Glass buildings. Who said glass building? He gets a star of the day. Right? I don't care how high performance your glazing is, it's not as good as a wall filled with insulation. What else is out there? Lighting can be, right? Decorative lighting. There's not a lot of decorative lighting in here. I've got pictures of, I have this thing about hotel ballrooms and stuff that we have all these ASHRAE conferences, and you look at that light fixture, right? You say, is that cost effective? I don't know, right? There's some that are more neutral, right? I bet that wood paneling costs more than drywall and paint. Is it cost effective? I don't know. Did anybody do that calculation? No. How about fountains? Fountains. Right? They consume water. They cost money. They use energy. And they're a maintenance nightmare. Do we have fountains? Yep, we have fountains. Why? They're pretty, right? The cooling effect. Does that really work in the Northeast? A couple months out of the year, somebody said. All right, but the point is that these are all decisions we make, right? How many of you know, right? How many of you drive Yugos? Right? How many of you have cars that have more than 2 speakers in them for your sound system? I saw a bike going up the road yesterday with a big speaker on the back of it, pointed towards the guy pedaling along, right? Does that help make the car go better? Yes. Yes. Throw him out of the building. Right? But the point is that we do things and make decisions all the time, right, that don't have to be cost effective, right? But they really become part of an integrated solution that get put together. Now, all right, so I've picked on number 2 for a little bit. Number 3 is saving money to save energy. In fact, engineers out there, you've spent all this time doing all this analysis in quadrant 1, and what happens? Value engineering pushes it into quadrant 3, right? And design today is about this vicious circle between those 3 quadrants in order to meet schedule, in order to meet cost, and maybe you think about energy goals as part of that, okay? And really, there are solutions out there, and one of the things that we've spent a lot of time studying is quadrant 4. Are there things out there where you can save energy and save money at the same time? We ran some computer models that had cost estimating software integrated with the energy models, and we said, computer, you go solve the problem. And no matter what building sector we picked, almost independent of climate, the computer could always find solutions in quadrant 4 that saved energy and saved money at the same time. Things like, reducing the amount of glass, right? Comes at a cost savings. Comes at a mechanical energy savings, right? More insulation in the walls, less mechanicals, right? Getting all these things to balance at the end of the day, the computer always found the solution. Now, those of you that think I'm picking on quadrant 2, you probably don't want to be in the buildings that quadrant 4 did, okay? Because basically what it did was it created buildings with a little strip of glass at the top of each room. Why? Because daylighting was highly effective at the end of the day, and you minimize the glass to minimize the loss, except the value of the glass for daylighting is higher than the heat loss and heat gain from that glass, right? You probably don't want to live in that space, and I get that. But at least we have to have this realization that there are those trade-offs, and that we're consciously making decisions, cost and energy and that the decisions we make have an impact there. If we can move along that line, the horizontal line, and maintain a constant cost, that becomes the value added to a project. And the idea is to try to focus on what's in quadrant 4. The building at the lower right was built with that kind of design philosophy. It's our office building in Golden, Colorado, built in 2010 or 2009. The building in the upper left is an old mill building, very typical of the northeastern part of this country. It happens to be located in Willimantic, Connecticut, built around 1900, so 100 years earlier. There's a kind of a magic point in time somewhere in the 1940s where air conditioning came to being, especially in commercial buildings, and it shifted the design philosophy of what went on. The building in the upper left, 1900, how did we cool that building? Natural ventilation, open the windows. Notice that the windows, long, narrow floor plates, good natural ventilation. How did we light that building in 1900? Same windows, right? Now, to the benefit of them, heating has always been relatively easy because of fuel sources, right? And so you could say, well, maybe the masonry actually helped with some of the daily temperature swings, right, and keeping the building cool. Cooling it at nighttime, closing it down, right? Heating was still a challenge on the energy side, but, designers thought, right, through all of these problems because they had no other options available to them, right? Notice how the building in the lower right, very similar, a little bit more sophisticated, designed with computer models that has the daylighting glass at the top. It's got natural ventilation in those little hoods. Those little hoods actually protect it from the high summer sun, right? All the glare inside is controlled. That building, the first phase, 240,000 square feet, right? Normal daytime lighting load is about 10 kilowatts for 240,000 square feet. So you can kind of do the math, right? Huge amount of energy savings in the lighting. By doing that, what happens to our cooling load? Goes to near zero, right? And so that building on the lower right achieved a 50% energy savings, did not cost a single extra penny to the federal taxpayer, okay? So I want to shift a little bit to how we're going to do this. How am I doing here? Okay. And talk about some things that are out there now to help think through these processes and make some of these decisions, right? So the first one is the Advanced Energy Design Guides. There have been a series of these over the last 20 years. They started with 30% savings, 50% savings. The last 3 were zero energy. And again, kind of on this collaborative spirit, who needs to get involved in putting design guidance together and how you put these pieces together, right? So US DOE paid for these in most part, right? ASHRAE, AIA, US Green Building Council, Illuminating Engineering Society, right? Teamed up to say, how do we put all these pieces together? And there was a steering committee that really guided this, made up of that membership, putting these together. The national labs provided some of the management leadership, the energy simulation, technical analysis, and the support that kind of went with that. And it is more of a guidance document, right? It doesn't have to be consensus-based like the standards, but it did have an open peer review, and there was a process to comment on the pieces in there. And so it's educational guidance, and I want to distinguish that from a lot of the other work that ASHRAE does. But the audience are people who, make decisions on buildings in getting them built, constructed, operated, right? That whole kind of delivery process. The intended audience really was those owners, architects, and engineers that wanted to do something better. And that's where it started at the end of the day. There are something about 700,000 of these out in circulation, either in paper form. Yes, you can still go to the ASHRAE bookstore and buy them in paper form. Or they're a free download from the ASHRAE website. And so there are 13 of them, starting with the 30%. I'd really focus on kind of the 50% and later. Now, when I had that fancy graph up there with the 4 quadrants, that value added was about a 50% energy savings. Interesting. NREL's building, which was optimized by an outside design build contractor to achieve our goals, was about a 50% energy savings. The guides are about a 50% energy savings, and even moving to the 3 zero energy guides, the codes got better. But what we also found is that, and some people say, oh, the codes are getting so stringent, I just can't do better than code, right? What we found is that the zero energy codes, even though the code shifted in the 10 years between the guide series, we still were 40 to 50% better energy performance-wise. Why is that? More technologies, better modeling and simulation, and ways to make these decisions at the end of the day. These guides talk about kind of definition and process. They talk about solution sets by climate zone. Lots of information. I think of it as kind of an idea book. Each one has like 200 how-to tips and strategies that you can use in thinking about design. A lot of that was driven by simulation to kind of look at energy use targets. Remember, the first thing on my list was set a goal, right? How can you set that goal? Well, one way is to go to these design guides and look at what goals have been set for those. By setting those goals, it really sets up this concept of a zero energy ready building, right? If I've got a building, and remember before I said about 2 stories, you can put it on the rooftop. As it gets taller, it gets harder to achieve that kind of rooftop powering the building. But there's no reason not to hit the same kind of EUI targets, whether it's 2 stories or 100 stories at the end of the day. And so we can talk about something called zero energy ready buildings, which really says they're so efficient, and this slide still looks at on-site renewables, but really that EUI target says, it is achievable to be zero by putting that PV maybe on somebody else's rooftop. Because when you get into things like warehouses, there's lots of excess energy available. And it really does talk about kind of this methodology that I put out there. Let's see here. So this is one of the zero energy guides, small to medium office buildings, and just some sample EUI targets for on the site energy side. Now, notice before I kind of said, if you're in the high 20s, what do you notice about these numbers on the office side? I really, for most of the climate zones, right, and most of you probably are in kind of the 4 and 5 area design-wise, are what? High teens, low 20s for design goals, right? And so set that goal and then say, what's it going to achieve? What do I need to do to achieve that goal? And guess what? Stay in budget and come up with solutions that actually go into what we called quadrant 4 earlier. In the guides, there's an introduction, perfect for building owners, the rationale for why we want to do this, and then it gets into some of the methodologies I've been talking about the last 15 minutes or so, building modeling, and then the bulk of it are these how-to strategies. And I mentioned that each guide has about 200 strategies. They're divided into a number of different topical areas in the guides. I encourage you, if you haven't downloaded one before, go download them and take a look at it. Lots of details, right? And some of it has to do with, one of the things that we recommend is that buildings today should be pressure tested, right? And it should hit certain pressure testing standards, right? And by doing that, because one of the things I think happens is the poor engineering community says, well, I really don't know how that's going to be built, and therefore I'm still going to oversize it because I really don't know how it's going to be built, and there's risk involved. Well, if you can reduce that risk on the sizing side by knowing that the envelope is going to be tight and built correctly and get detailed properly, that enables you to really think more appropriately about the sizing of the equipment. Sizing has a relationship to cost, right? Both electrical and mechanical. We talk a lot about what that looks like and drawing what I call the red line. Get out the set of plans and draw the red line, where that barrier is and make sure that it is continuous. The guide also has case studies in it. These are, this one happens to be in Boulder, Colorado. And it's a little bit of a chicken and egg problem here, right? Because we're looking for case studies before the guide came out. But the object was, can we find buildings out there that have achieved similar EUIs to what's predicted? And so this is one example of that. This is another one that actually got a lot of press when it came out. Very low EUI on this building. And notice this building is zero energy. And notice that they got there with how many floors? 1, 2, 3, 4, 5 floors. And then they kind of have the, now, you could say, is that architectural? I guess I'll have to ask Zach. Is that architectural or is that functional? Both, right? And that is part of the answer. I didn't prompt him to say that either. It also talks a lot about some of the systems. When you get into the multifamily guide, especially, one of the things that it has a lot of information about is domestic hot water, because it dominates the problem. I've heard of a lot of multifamily saying, oh, I solved the HVAC. I put in some heat pumps, right? Here's my heat pump paper. But I didn't deal with the domestic hot water. Well, that's 30% of the load of a lot of these multifamily buildings. And so there are definitely strategies in there on how to think about that. So there is kind of a pathway to think about here, right? Set the energy goal, right? Reduce plug loads. Oh, plug loads. That's not in my scope of work as an engineer or architect, right? But what happens if you help the client think about the plug loads? Right? Do you really need 4 watts a square foot for plug loads? And when we go out and, interesting, when we go out and measure them in office buildings today, it's about 10% of that. How much of a difference would that make on the HVAC? Knowing that information, working with the client on some of those pieces. And I realize it gets really complex when you start getting into leasing agreements, right? I admit that. Reducing the lighting loads, right? Daylighting, other strategies. There is guidance in there for what the lighting power densities are. And again, if the lighting designer can meet those lighting power densities, that impacts the HVAC on the other side. I already mentioned then looking at the thermal envelope of the building, right? Testing it, making sure it's tight. View glass is important, right? I'm not sure we need 100% glazing. But typically, it does fit into quadrant 2, right? That was the spending money, wasting energy category. And interestingly, today, it's not all about the glass. It's about the frames are one of the key pieces on that you really have to pay attention to. And then if you can think about it, natural ventilation, right? And it's like, well, how much can you do? You got to worry about fire, especially when the buildings go this direction. But it is still could be a consideration. And interestingly, I worked with a school after Katrina in New Orleans. 1912 was the construction, 3-story, double-loaded corridor classrooms, right? Very classic of the architecture of that time. Again, 1910, right? No air conditioning, New Orleans, sounds delightful, right? But it was interesting, it was after the hurricane, it blew out the power, the winds had blown out the windows, somebody had come in and dropped the ceilings to 8 feet, probably calling it energy efficiency or something, and blocked the upper half of the windows in order to do that, right? It was 12-foot ceilings, right? And we went into that building, no power, nothing. I want to say it was like October, November, and it was beautiful. The breezes were going through the building. The daylighting was spectacular in this space because the wind had also blown out all the ceiling tiles in it. And you have to go back and say, how was that building originally envisioned? And can we imagine that, in the same way, right? In thinking about it in terms of energy, it had transoms over the doors, right, to get that air moving, through the space. And really stepping back and saying, what can this space be like? And you say, people laughed earlier, right? What do you think of with New Orleans, right? Humidity, big problem, right? But what happens between October and April? right? The climate is probably pretty conducive to a lot of just natural what happens in the climate. And yes, the summertime, you want to think about something else. You definitely want to make sure you keep the mold out and all those other concerns. But there's a significant part of the year where you could just kind of turn off the building and let it do its thing because it was designed to do that. Oops, I guess I didn't get to the bottom of my list here. So after the envelope, HVAC selection, sizing, and then renewable system, give it a margin, right? So I'm debating. I used to use a bridge example. I don't know if that's a good idea anymore. If you're designing a bridge, do you design it just enough to hold the trucks that are going over it?
Clearly not.
Clearly not, right? And so if you want it to be zero and you're really committed to that, don't match the renewables exactly to the building. Give yourself a buffer if that is what is important. If this environmental emissions discussion are what's important. I talked before about some of the EUI, it's kind of the interesting things. So there are 3 versions of 90.1. And you notice the bars where the 30%, 50%, and the zero energy guide for K-12 schools set. And each one went down. But even though the 30% was 30% better than 2004, which isn't even on this chart, by the time we get to K-12, substantial reduction in energy, still this one I think was 42% savings in 2016, which is what it was based on. All right, so we have to make a little shift here because you say, well, I've got all of these renewables online and I can talk about this balance, but what happens when the sun's not out? I got some fascinating graphics that didn't make it into here, obviously, of the eclipse, both on the Texas utility grid and even my own PV system at my house in Connecticut. But if you really need to solve the problem, we have to think about 100% renewables 100% of the time. I already said the grid looks the way it does because of building loads. We need to start thinking a little bit more about this time dependency part. Energy storage. Do you get any benefit from energy storage from a BTUs or a kilowatt hours going through the meter? No. But that's what we're measuring, right? And so the metric that we're using to measure things like storage always shows it as an energy loser, right? Now, what can storage do for us, though? Right? Even think about yourselves, right? I am now holding you up from the break, right? And my guess is that your body, is storing energy, and you're like, oh, I'd really like one of those muffins out there, right? You don't constantly eat muffins. Well, you probably shouldn't constantly eat muffins, right? But that's stored energy sitting out on the table outside. You're going to consume it, and your body's going to store that energy so you can keep going, right? Energy systems need the exact same thing, don't they? All energy systems have storage. Where is the storage today in the power system to keep it reliable? Right? There's a coal pile, there's an oil tank, there's a gas well that is the storage of that system. Where's the storage for solar energy? About 93 million miles away, right? And the problem is that periodically, right, I mean, the big event was last week, but periodically we have an interruption from that energy source, right? It's called the Earth rotating, or in the Northeast, lots of clouds, right? And so storage really is the solution to help us with that, but also think about where is that storage. It would be great if we could get buildings to only use energy between 10 and 2 every day, right? Today, between 10 o'clock and 2 o'clock, we are going to use lots of energy, right? And then it's going to shut off, and we have to figure out how to make the building operational the rest of the time. If we did that, and if there were huge demands for electricity between 10 and 2 every day, how would the grid respond? How would the grid planners respond? they'd put on more renewable energy, more PV. It's cheap to put on buildings or in fields, right? That is how they would respond to that. And so we really need to think about how do we align that production with the grid, right? And the solution to that is storage. And I will say there's a whole nother talk about, the closer the storage is to your end use, the more resilient the building is at the end of the day. Maximize the use of energy between 10 and 2. And the problem with buildings today is they don't do that, and they use a lot of energy between 4 and 9 because office buildings are still running, residential buildings are ramping up. How do we meet that load between 4 and 9 today? You put a new building online. We talked about the 34, New York cities coming online, right? And they start using more energy between 4 and 9. How do we meet that load? Burning something, probably natural gas, right? And so that's back to these two going together. And so we really do need to kind of think about how we're designing buildings for the future of that. So existing buildings, pretty briefly here, is that there's you can create action plans. What do you want your building? Remember I started with what do you want your building to look like in the future? Create a plan for how it's going to get there. We spend money on buildings every single day for maintenance. When you make a maintenance change to a building, and it could be as simple as what color are you going to paint the ceilings, right? Does that help the energy performance or hurt the energy performance? And if you plan those things up ahead of time, it makes a huge difference. If the hot water heater, the gas hot water heater in your house dies today, do you know what you're going to replace it with? And you say, oh, I don't have electrical service for that. I don't have blah, blah, blah. I don't even know what products are available if I wanted to switch that to a heat pump. And so what's the immediate reaction? Call the plumber and get something in there today, now, and guess what it will look like? The exact same thing you had before, and now you've made another 20-year investment with the same problem of the last 20-year investment. If you create a plan to think about how to move forward, so when that dies, put an asset tag on it, if you're in a commercial building, and say, yep, I've got the spec, I know what to replace it with, and that's what's going to happen, right? Can make a huge difference here. I'm going to skip through this. I already talked about the kind of version 1, which was the just straight balance, versus version 2, which is really thinking about what this alignment is and aligning with zero carbon sources on the grid in order to make my zero energy building really a zero carbon building. Here's an example of kind of this renewable curtailment. This is California. Every year, or especially this time of year, California is throwing away renewable energy because nobody wants it between 10 and 2. And if we can create a market for that and you can store it locally, it's almost free for the asking. So when people start talking about the cost effectiveness of some of this stuff, this is kind of the wave of the future and how to think about energy storage. So what can we do, right? 70% of energy goes into buildings. The grid looks the way it does because how we've designed them in the past. But we can start thinking about reducing the loads, aligning the buildings. The perfect scenario is that the building has assigned to it renewable energy to match its consumption, right? And that really starts getting at the zero carbon discussion. So, you're all decision makers, right? How do the decisions you make going to influence the future of building design, and how creatively can you do that? And then some of it is, can you do that and provide it as a value-added product to your clients? The other piece is the opportunities are when somebody says, I can't do that, costs too much, and you may say, oh, that's going to cost you too much money. You can't install a heat pump, even though the paper now says you can do it, right? How are you going to get over those barriers? What are the solutions that you need to get over those barriers? And together, we can really think about how building is used in buildings and change that, right? You have the ability to make this happen at the end of the day. We are putting out the zero energy, or the decarbonization guide for thermal systems, AKA heat pumps. That is ready to go. It's actually going through its final editing this week. We also spend a lot of time talking about these things, right? I asked the question, like, what is stopping you from delivering zero energy, zero carbon buildings today? And whatever your answers are, those are the barriers. And so we actually put cohorts together to kind of discuss about that and come up with what your challenges are and how to deal with that. Because otherwise, we don't get to the finish line. So there's your credit thing. I will stop there.